All right, in this lesson we're looking at rational functions still for Unit 10 here, and we're looking today at end behavior and horizontal and slant asymptotes. So, finding the end behavior, which we talked about this end behavior before, for example in our unit on polynomials. But the end behavior of any function is simply determining what happens to the function as x approaches negative infinity. That's how we read that, the symbols there. And where x approaches positive infinity. So in other words, all the way to the right on the graph and all the way to the left. That's what we're looking at. What happens to the function values as x approaches either negative or positive infinity. So example 1, from the charts, determine the end behavior of f of x and sketch the end behavior on graphs. Okay, so this is where x approaches positive infinity. Okay, I'm going to write the little approaches arrow positive infinity, and over here it approaches negative infinity. So we notice again x is going to positive infinity, and our y values, the function values, are approaching 12 there. And then I look over here as x approaches negative infinity, so going to the left on the graph, my y values, the function values, are approaching 12 as well. They're approaching 12 from above here, and they're approaching 12 from below here. So when we make this sketch, we'll put in coordinate plane here. Whoops. There we go. And if we look at the values, we need to put in what's going to happen here. We're approaching 12, so I'm going to put in a dashed line here at 12. That's not actually on the graph, but we want to label that. So we're not sure what's happening in the middle, but the end behavior, so the far right part of the graph, that would be this section here. As x is going to positive infinity, we're approaching 12 from below. So we're at 11, and then we get closer and closer and closer, and it does this. So as x goes out here to positive infinity, y is approaching 12 from below. Okay, now this part, as x approaches negative infinity, so that's the far left side of the graph. We see that our function values, the y values, are approaching 12 from above. See, they're at 12.4, then 12.1, 12.002, etc. So they're coming from above like this, and it's going to hug that horizontal asymptote for the end behavior as x approaches negative infinity. So that means we have a horizontal asymptote, we'll abbreviate HA, at y equals 12. From the table values, we can tell that's what's happening. As x approaches infinity and negative infinity, the function values approach 12. All right, example 2 says, determine the end behavior of f of x equals 4x over the quantity x minus 5 by creating two tables, one as x approaches negative infinity and one as x approaches positive infinity. That is the end behavior on a graphing calculator. So I'll make those tables and then we'll analyze them. All right, so here are the tables. I just went into table setup and put my independent variable, the x variable, to ask, and then I was able to type in these values. So to simulate going to negative infinity here, I put in negative 10, negative 100, negative 1,000, negative 10,000. So as x approaches negative infinity is this table. And then over here I did the same thing, set the independent variable to ask, typed in 10, 100, 1,000, and 10,000 for the x values to simulate x going to positive infinity. So we're analyzing what is happening to the function values, the y values, as x approaches negative infinity and positive infinity. And we can see that the y values are approaching 4. So that tells us that we have a horizontal asymptote at y equals 4. We'll abbreviate horizontal asymptote with y equals 4. So you can see as x approaches infinity, the function values approach 4, f of x approaches 4, and as x approaches negative infinity, the y values approach 4 as well. So that tells us we have a horizontal asymptote at y equals 4. All right, so now that we have the horizontal asymptote identified, it's good to write out the end behavior in infinity notation. So we would write it this way. F of x, the y values, approach 4 as x approaches negative infinity. That would be this part. And then over here for this table, f of x approaches 4 as x approaches positive infinity. And you could put plus or minus right here and just write it once since it's the same in both cases, or you can write it in two ways. So in a college level math class, you will start using limits to do this, but this is called infinity notation, and we'll stick with this currently. It says sketch the graph produced on the calculator and show the horizontal asymptote. So we'll do that next. Alright, so I have the function 4x over the quantity x minus 5 in my calculator here, and when I graph it, this is what I see. So I can barely see the upper right part of the graph, so this is a good opportunity to go in and change the y max to something larger and the y max to something larger, so I can add some room to this upper right section of my graph, and we can see it a little better. So we'll just use this graph. You could sketch this obviously, but we'll actually just bring this graph over and work with it. So it says sketch the graph. Okay, here's the graph, and show the horizontal asymptote. Alright, well, it's probably a good idea that we sketch in the vertical asymptote as well, because we can see that, and we have discussed that in previous videos. So there's a vertical asymptote right here, and then there's a horizontal asymptote right here. So we have already determined that the horizontal asymptote was at y equals 4, so we can label that as 4. And from our prior knowledge, we know we have a factor of x minus 5 in the denominator, so that actually gives us a vertical asymptote at positive 5. So there is our sketch. Main thing, we notice that we have the horizontal asymptote at y equals positive 4 right here. Alright, now on to example 3. It says put the function of example 2 in proper rational form. So example 2, what the function was f of x equals 4x over x minus 5. Proper rational form, if you recall from our first lesson on rationals, it says that the degree of the numerator has to be less than the denominator. So I have a degree 1 here, degree 1 in the denominator as well, so they match. So I need to fix that. We can fix that through long division. So I take the 4x and I divide it by the x minus 5 factor. So what I need a 4 here to get a 4x here. Alright, I need some more room. So let's move this over. There we go. Okay, so 4 times negative 5 is negative 20. So I would have a plus 0 right here. So the 4x cancels. 0, I'm subtracting here, plus 0 minus negative 20 is a positive 20. So I have nothing left to bring down, so my remainder is 20. So I have 4 plus 20 over quantity x minus 5. So now it is in proper rational form. So it would be 4 plus 20 over x minus 5. So once it's in proper rational form, your horizontal asymptote will be the section in front of the remainder. And the reason that happens is, analyze what happens as x approaches negative infinity and x approaches positive infinity. So let's say, let's do this. So 4 plus 20 over, let's substitute in 100,000 for x. So 20 divided by 100,000 minus 5, that's we're dividing by a really big number. So that's really, really small. So the bigger that x gets, the closer this thing gets to being meaningless, because we're dividing it by a huge number. So it basically goes away. So as x approaches infinity, we get closer and closer to 4. That's why we have a horizontal asymptote there. Same thing occurs if I put a negative symbol here as we approach negative infinity. So put in negative 100,000 for x. So we're still dividing by, it's a negative, but it's still a large number. So when the denominator is huge, as it goes to positive or negative infinity, we are dividing by a huge number. It doesn't matter if it's positive or negative. Dividing by a huge number makes this more, and basically makes it meaningless, and we're only left with the 4. So that's why as x approaches positive or negative infinity, our y values approach 4. So based on this analysis, what is the end behavior? Well, the end behavior is that we have a horizontal asymptote at y equals positive 4, which we've already identified, and we have just shown that using putting this in proper rational form to see what actually happens as x approaches infinity and x approaches negative infinity, which is the definition of end behavior. And also recall, for the end behavior, we can write it like we discussed earlier in the infinity notation, which would be f of x approaches 4 as x approaches infinity, and f of x approaches 4 as x approaches negative infinity. And that was our symbol way of writing it in infinity notation to describe what is happening to the end behavior, and then also that tells us that we have a horizontal asymptote at y equals 4 based on this information. All right, now let's go to example 4.